So today we'll talk about principle of minimal action and about Hamiltonian and about Legendre transform that transforms functional for action to Hamiltonian. So, but let me start with variational problem. So, simplest variational problem is the following. You need to minimize a functional, which depends on the unknown function u, and this function u minimizes integral of some function f, which is assumed to be differential function of x, u, and u prime, and the values of u in the boundaries are known. So that's a variational problem, and the first examples include brachistochrone, which is the curve of steepest descent of the curve that the trajectory that minimizes the time of the travel between 2 points under gravity, or the shortest path around the cylinder. If you have a cylinder, you need to go from one point to another, and what is the shortest trajectory, and so etc. So so for whatever physical meaning of this problem is, the minimizer, if the minimizer is smooth and if it exists, it satisfies the following equation, which is called Euler-Lagrange equation, and it is here. So this second-order differential equations, derivative of f with respect of u prime depends on u prime. When you differentiate it one more time, the second derivative of u appears, and so that's the equation. That's this equation called stationarity condition, and this on the left-hand side called variational derivative. And this condition is similar to the stationarity in calculus. The derivative of function is 0 if x is the minimal point. And as in final dimensional case, stationarity selects functions that can be minimizers, but stationarity alone does not define a minimizer. The function, for example, the function that maximizes the same functional satisfies the same equation. It's the same like in calculus. Derivative is 0. It could be minimum, could be maximum, could be neither. And the minimizer might have equation for minimizer might have several solutions. And for example, the stationarity. If you look on the problem of shortest path around the cylinder, the stationarity proves that the shortest part is a helix. But there are two helices, clockwise and counterclockwise. And stationarity allows both. And the question which part is shorter is defined by additional consideration. And if you move the target point, then suddenly the clockwise trajectory will be replaced by counterclockwise trajectory. So the minimal could jump from one solution to another. But both solutions satisfy the stationarity condition. So now what is action? What is action? Lagrange, who derived this first equation which we discussed, immediately noticed that Newton's law of motion of any particle with mass m, this law of motion, is equivalent to a stationarity of some functional, which he called action. And the stationarity is nothing but the difference between kinetic energy and potential energy. Kinetic energy is, as we know, this half m multiplied by square of derivative, and potential energy is antiderivative of the force F. So if we substitute these expressions into Euler-Lagrange equation, we got the right equation of the motion. And so, always in this problem, we need to assume that the initial point is point in initial time. Coordinate of initial point is given, and coordinate in the final time is also given. Now, this is a little bit different from the equation of motion, which are usually used. And in the last case, we know that initial position and initial speed, and then we follow the evolution of the motion. In this case, we know the starting point and the end point in the past and in the future. Okay, but so there's an example. We know the equation of harmonic oscillator is this, u double prime plus u is equal to 0. Here for brevity, we assume that omega, the frequency is equal to 1. And the Euler-Lagrange equation, this is the Euler-Lagrange equation for the following functional: 1/2 u prime square minus u 1/2 u square. So if you do Euler-Lagrange equation or apply Euler-Lagrange equation to this functional, we obtain the solution. And the solution is written here as we know it satisfies both Euler-Lagrange equations and initial conditions and final condition, initial and final points. So after this thing was discovered, people proclaimed that action is minimized on the trajectories, and this was like a big deal philosophically, because this would prove that our world is in some sense the best of possible world. All motions minimize something. Well, beginning of 19th century, this idea was quite popular. However, the action is not minimized. The action is stationary solution, but not necessarily a minimizer. And to show it is enough to look on our example. Since we know u, we could substitute this u into action and compute first this Lagrange and this expression under the integral sign. So derivative of sine is cosine, and then you have square of cosine minus square of sine, or cosine to t divided by sine to, actually s here. I'm sorry, I misprinted. And then the action is actually just when we integrate cosine, we get sine to s in the end, and then because sine is product of sine and cosine, one sine cancels, and we got cotangent s. S, I remind, is the end point of the trajectory. So when the final time of the trajectory moves and approaches pi, the action cotangent approaches minus infinity. It must be minimized in the trajectory. Well, I mean, if you look at the graphic of cotangent t, we'll see that it's large in the beginning. Why it's large? It's large because if we want to, in very small time, to put my mass from point 0 to point 1, to have a lot of speed, right? So at the beginning, this kinetic energy should be very large if the time is limited, and I need to put it from 0 to 1. But then it decays, and on the time, this half p, it goes to minus infinity. After this, cotangent again jumps to plus infinity, but doesn't make any sense. And clearly that if time is larger, then you can do something better than infinite action. For example, you can just do not move for a while and then start to move later, and make this action as small as you want. Which means that so for long trajectories, this principle does not work.
Okay, that makes sense actually.
Okay, so this is similar actually to what like we observe in geodesics. If you start from the North Pole, and you want to find the shortest path, you go to a long meridian, right? And it's optimal until this point reaches South Pole.
Yeah.
Here we have infinitely many meridians, and if you pass over, then this path is not longer optimal, another path is optimal. It's something similar, actually. Yeah. This argument actually used, by whom? By Columbus, when he wanted to go to India from the other side. So it might be a shorter path. And unfortunately, he jumped into American continent. He couldn't prove. I mean, this idea is that action is not minimized, actually is more deep. The minimal action principle would contradict the causality principle, because the future destination cannot influence the motion in the previous time. So the future cannot affect the past. And from formal viewpoint, the minimum of long trajectory might be disproved by special test called Jacobi test, which basically compares this stationary trajectory with slightly varied trajectory, but variation is not local. It just finds the best local variation. That's non-local variation. Yeah. So the question remains: why is this minus in the expression for action? Kinetic energy minus potential energy. We know that these two parts of the energy, and what it's not clear what is the physical significance of the difference between these two passes. And surprisingly, the answer was given by special relativity in 1904 by Albert Einstein. He used the formalism developed by Minkowski spacetime. So according to special relativity, the particle minimizes the relativistic energy in its own time. So I have to explain what is relativistic energy and what does this mean in its own time. Relativistic energy differs from usual Newtonian energy by adding one term. This gamma m is the energy of the mass at rest, and it is some constant which is inherited to the mass, and it does not change when the mass moves. It just stays still. But the time on the particle and the time of external observer via external observers is different in Minkowski spacetime. And the time in the particle is related to the time, the small instance of time in its own particle's time is different from the time instance of time that we observe by this factor 1 minus u prime divided by c squared, which if we extend this into Fourier series, Taylor series, and notice that this difference is very, very small, we could just obtain this expression 1 minus, should be u prime again, it's misprint, sorry, u prime squared divided by 2c squared plus something smaller. Now, if we substitute these two expressions into this product, we will get that expression, and then we multiply point by point, multiply by 1, we have these two terms, then multiply first term here by u prime, should be prime square, by c square, and got this term, and then something else which is smaller. Now, if finally, if we make this constant gamma, previously undetermined, to equal to c square, square of square of the speed of light, we obtain this the formula that the energy is mc square plus potential energy minus kinetic energy. So kinetic energy is basically the shadow of the changing of time. It's absolutely, I mean, it's amazing, right? Yeah. So by these assumptions of special relativity, we simultaneously obtained this famous E equals to mc square formula. And the sense of this formula is that because of that constant, we get the kinetic energy. So kinetic energy is mainly a mirror and fiction in sense of related to the difference in times in the particle, in the moving particle, and in the observer. So that's what that explains this difference P minus T. Then this first term is constant, and we can vary it or not vary it. It does not. I mean, when we find the optimal solution, this term remains constant and it does not affect the trajectory. So that was the first part. That is the first part. Now let's talk about Hamiltonian. Well, we have Lagrangian mechanics, which explore this equation, and also very often use Hamiltonian mechanics. So what is Hamiltonian mechanics? Hamiltonian mechanics basically is just a different way to express the same equation of motion, like in Lagrangian mechanics, basically in different notations. These notations are more convenient in many applications. So to start with, what I want to do, I have the second order differential equation, and I want to replace the second order equation with two first order equations, which are solved against the derivatives of two unknown functions, z1 and z2. And if u is a vector, then z is also a vector, z1 is a vector, z2 is a vector, they're all n-dimensional vectors. So for vector u, instead of n second order differential equations, we will have 2n first order differential equations solved for the derivatives. This form is convenient because, see, unlike the variable z, z1 and z2 are continuous and differentiable. If f, usually the forces are bounded, then the derivatives of this variable z's are bounded. But not. But in one-dimensional case, you also have this exceptional idea that all derivatives are on the right-hand side and all the functions on the right-hand side. And why it is important? Why p is better? Not better. Why pi is convenient, I would say, because see, derivatives of both of these quantities are known functions, and very often they could be bounded. If they're bounded, derivatives are bounded. You have continuity. Derivatives could jump, whatever, but still the functions are continuous. So if we average, for example, we could replace fast oscillating with the averages. This allows to use standard methods to compute and standard methods to analyze the system. So to derive the system, we can do the following. We could look on the original problem and treat this u and derivative of u, v, which we called v, as two independent variables constrained by the relation that v is equal to u prime. And then we use Lagrange function p to account for this constraint. So instead of original variational problem, we end up with constrained variational problem, which has this form. We have maximum for this Lagrange multiplier, Lagrange function, minimum for two variables, u and v, integral from x1 to x2 of some Lagrangian, which depends on x, u prime, and v. And this Lagrangian has the following form. It is this original function f that we wanted to minimize, plus p multiplied by this u minus v. So this is two equivalent form, and when we to analyze the problem, it is convenient to integrate by parts this first term pu prime, and we will have pu prime is equal to p prime u. Oh, again, it should be not prime. P prime u, and then integrand of this Lagrangian will be f p prime u minus p v. V is u prime instead of that term p u prime. Instead of p u prime, we have minus p prime u and then pv. And then find stationarity condition. The Lagrangian, this L cap does not depends on derivatives u and v, so we can just Euler Lagrange equation degenerate into these simple relations, and derivative with respect of p return the constraint. So I have three equations for three unknowns, u, v, and p. Three differential equations. Two differential equations, one algebraic relation. So finally, what we need to do, we can, first of all, we could say that we could prove that this system is equivalent to original one. If we differentiate first equation with respect of x, we have d of dx of dv, and it will be equal to p prime, and also it will be equal to df du. So this as in original Euler Lagrange equation. So this is why the system is equivalent. And what we need to do to go to canonical system, we just need to do one operation. We need to exclude v. For this, we can solve the first equation for v. This algebraic equation, which defines p as a function of v, and we want to find v as a function of p and the rest of variables. This is possible if this operation is possible if df du is monotonic, or if the antiderivative f is convex with respect of the variable v. We could try to exclude all derivatives. For this, we need to solve this equation for v. Is it possible or not? Well, when it's possible. It's possible when this this function df dv is monotonic with respect to v, which means that f is convex with respect to v. So after we do it, we could just substitute this founded relation into the last two equations, and we found this system of equation. You see, instead of u prime here and there, I just put this function theta that depends on x, u, and v. So we have now these two variables p and u. They both differentiable, and the system is take that form which we got. So that is standard. That is Cauchy form of Euler Lagrange equation. Now, what is Hamiltonian then now? Having this form, we would introduce a function that we call Hamiltonian, and I write this function for vector minimizer u, which then it will be just sum of scalar product of vector p and vector theta minus f of xu, and instead of u prime, again I put theta. And here also the theta is instead of u prime. And then one could check the remarkable, so the features of the Hamiltonian, that if you differentiate this expression as a compute partial derivative with respect to ui, we got pi. And if we differentiate this thing with respect of pi, you got minus u prime. U prime. So p prime is so very symmetric and nice relation. And so if this Hamiltonian is independent on t, then this h is constant along the trajectory. So this is an example why how to obtain this. So I just take this one. So it just do this computation, and all terms cancel, and finally we got the right expression. So what is convenient? Hamiltonian is an algebraical function. It doesn't involve any derivative. So you just define this function, and you know dynamics of the system. In say atomic physics, in order to explain the behavior of a particle, is conventionally to write the Hamiltonian of this particle, and all the weird behaviors will be just derived by just simple differentiation of this Hamiltonian. If Hamiltonian is independent on x or in time dependent on time, then it is constant. So that's the advantages of using Hamiltonian. So that in dynamical system, if we just look on this minimizing functional in this form, kinetic energy minus potential energy, and kinetic energy has this form V, AV, and then we could find that impulse P is A W. We solve this equation for V, say V is A minus 1P, and substitute into the expression for Hamiltonian. We will have this, the first term, P multiplied by this V, and minus kinetic energy minus potential energy. And you see that this first term is double the kinetic energy. So when you just cancel, we just, we subtract double kinetic energy variant from double kinetic energy, then we have this expression T plus P. So Hamiltonian in the time dependent in dynamical problems is equal to the total energy of the system, kinetic plus potential energy. And if Hamiltonian is independent on time, total energy is constant, and the process is reversible. We could move, like in a wave process, you can just look on waves propagating to the left, propagating to the right, and satisfy the same equation. One example, harmonic oscillator. We compute V is equal to P divided by A, and substitute this expression into Hamiltonian, and Hamiltonian is the square of P divided by A and plus Bu prime, kinetic energy plus potential energy. And from here we can derive canonical system as we stated. So the system is rather simple. So that's Hamiltonian. And finally, just I want to talk about Legendre transform. So to obtain Hamiltonian, we need to solve, as you remember, this equation, solve equation. Let me go back. Solve equation, this equation for for v. So instead of having equation for p as a function of v, we want to have v as a function of p. This transformation is related, is called the Legendre transform. So Hamiltonian is Legendre transform of Lagrangian. So what is the definition of Legendre transform? G of y is the Legendre transform of a convex function f of x if g of y satisfies this equation, maximum with respect of x, xy minus f of x. So for example, if f of x be like a by half x squared plus b, then in order to find the Lagrange transform, we could first maximize this expression xy minus f with respect of x, take a derivative, and obtain y is equal to x, or x is solve it for x is y to a, and substitute back to that expression, and we will call this 1 over 2y minus b. Just notice an interesting thing. If I add any constant to this f, this constant will be subtracted from g. So some of them are independent of the constant. What properties are? Well, for if function f is convex, the Legendre transform is an involution. So if f is actually maximum with respect of y, and we have the same expression, but instead of f of x, I substitute g of y, instead of x, I substitute y. So involution means duality. Involution also means that no information is lost during this transform. Since we can recover the original function, we use the same information in the transform. Transform содержит all the information of the function as the original one. Also, we could find this peculiar relation that the product of second derivatives is always 1. Which means that if function f is, say, has a flat part or almost flat part, then its derivative, second derivative is very small, then the second derivative of transform is very sharp at that point, and this flat part will correspond to the vertex, to the angle in the trajectories of g. And of all involutions, f, there is some stable point. So if f capital of x is x squared by half, then g capital of y is y squared of half. So stable point is typical for dual relations. So finally, what is geometric meaning of this relation? So let's consider a monotonic relation. Y is equal to f of x, and assume that relation that is monotonic, so derivative is bigger than 0. And then we defined what we call energy or antiderivative of f. So that the derivative of f capital is f lowercase. So then, therefore, this means that the solution of this relation is a solution to the problem maximum of xy minus f capital of x. Indeed, when we just differentiate in respect of x, we got y is equal to derivative of f, which is f lowercase. Then, so f is antiderivative of that relation. Then they define the inverse relation, and we could invert this expression, and f of y should be of y, of course, and find its antiderivative. And then the relation, the inverse relation, is solution to that problem. So basically, Legendre transform of f and Legendre transform is G are two antiderivatives, which corresponds to solving the original equation for y or for x. And finally, I need to just draw some picture. So suppose it's my f of x. Y is my f of x. Or another for example, say that x is g of y. If I look, so the area under this curve is f capital of x. So if I inverse this relation, I basically change the position of axes x and y, and the antiderivative of that y is g of y, is the area to the left of that curve. And from here, we could say that f of x plus g of y is equal to the area of that rectangle, xy, or g of y, if you want, is xy minus f of x. And the same is true for other one. So that's the symmetric relation which corresponds to this relation. What is important here? F being antiderivative is defined up to a constant. We could add a constant to f without changing anything. But then, as we haven't seen before, if we add a constant to f, we subtract the same constant from g. So the sum of them is defined completely and is equal to this product x and y, which could be treated as a work of external forces. So this xy is measurable quantity, unlike energies. You cannot measure the energy, you can measure only difference of energies, but you can measure the forces. So some of them are measurable, and that's important. Now, finally, in dynamics, P, in dynamics, dual variable P is, which is analog of Y, is linearly depends on variable V, which is analog of X. So in dynamics, this curve is straight. And because of this, the areas of two triangles are equal to each other. And so energy is equal to complementary energy, and each of these energies is 1/2 of the work of external force. So that is the feature of dynamical problems. In In other application, other physical application, F could be not linear. I mean, it could be any constitutive relation like force versus elongation, current versus voltage, etc. And this curve could be monotonic, but not necessarily linear. And then these two energies and complementary energies are not equal to each other, but the sum of them is always equal to the work of external forces. Well, we have, because, I mean, Lagrange Legendre transform has a lot of properties, and some of them are just geometrical, some of them are physical, etc. But that's probably I stop here. Yeah. So just to summarize what we have done. We look on simplest variational problem and Euler-Lagrange equation. Now, for dynamical problem, Newton's law equivalent to stationarity of the action. Action is not minimized in general. The structure of action, the difference of two energies, could be explained from the viewpoint of special relativity. It is because of change and because of relativity of time, and because of what Einstein suggested, that this E equal to mc squared, that energy which is inherited for a mass. And Hamiltonian is so it would be nice to have. We want to. For many applications, we want to transform Euler-Lagrange equation into Cauchy system, into the system solved for derivatives. And to do it, we can solve the problem for the derivative of the minimizer and introduce Hamiltonian, which is convenient form of writing these equations. And it is equal to the, in mechanics, sum of potential and kinetic energy. This transform from Lagrangian to Hamiltonian is performed as a Legendre transform, which is just a mathematical way to transform one function into another one. This transform is an involution, so we could look on the same function from two different viewpoints, equivalent, and and you can from function you can define Legendre transform, and from Legendre transform we can return back to function if the function is convex. If the function is not convex, then something is lost. And the geometric property of this Legendre transform is that that these functions and its Legendre transform are both antiderivatives of some relation that either y is a function of x or x is a function of y, and for this reason they're equivalent. And the work of energy, so that sum of function and its Legendre transform is equal to the work of external force as a product of x and y in this case. So that's the main features of this Legendre transform.
Can I ask a
Sure.
Can you remind me, is this this time dilation factor, this relativistic constant that depends on the velocity, this is due to the underlying space-time metric?
Yes. Yeah, Minkowski geometry.
Right, it's just the Minkowski
geometry.
metric.
But it also could be found from just thought experiment. If you have the source of some signal and you move from the signal in the speed comparable with the speed of light, then what you observe in every moment of time is not the signal which is emanated in that moment, but the past signal, the past which was emanated in the. So if you have just, suppose the time has moved with some speed and you move a little bit slower than this, so you watch all the time the past. And so this difference, but in the same time, if you measure the time in your just hand watch, this will be not affect. I mean, the motion, it doesn't affect anything. So then we have two different times, and part of it is this the red shift in the on the astronomy. You see the
Yeah, so I'm a little bit confused because now it seems like in the relativistic case we're just minimizing the proper time of a world line, right? And those are the geodesics. But how do we introduce like kind of motion that's described by like forces, for example, in space-time? Because it seems like we can account for forces in the model T minus V, right? When we're doing the classical mechanics, we can account for forces on the system as long as they're conservative.
Sure.
However, when we bring it to the relativistic case, it's not clear how we can model a system with relativistic forces. It seems like because we're putting, we're just minimizing the proper time of a trajectory, right?
Yeah, but if the forces are, say, depend, say, on the distances between 2 points.
Oh yeah.
They're not affected by this, right? Like, if you look on celestial mechanics,
Yeah.
so I mean, basically the force is just directed from one body to another one, and is proportional to the one over square of distance.
Yeah.
And you can move as you want, but it's still the same. If the forces are time dependent, I frankly don't know, but it definitely should be put this time of the particle into the expression.
Okay, so correct me if I'm wrong, but I think I figured out what I was trying to ask, which was that we begin with this relativistic potential, and then we just add this constant term, a constant multiple of the mass, right? And we minimize that over the time. So the term of the potential that besides the constant term that we're adding, like the original potential term, that can account for conservative force space-time forces, right?
Yes.
So that force, that's really where our forcing term comes in, and our force would be like the negative gradient of the potential, right?
Yes. Yes. So if time is not varied, if time is constant, then this first term will have no effect at all. Because you can minimize quantity, you can minimize some function, you can minimize this function plus a constant. It does not really matter. So but the intersection between this additional mass and tiny change of the time could make a difference if this additional term is very large. Then multiply by the small fraction of time. So this is why it's mc squared. It's huge. Multiply by this tiny change of the time, and it gives kinetic energy. That is, but that is strange, I agree. I mean, that's what it is, yeah.
Okay, and then the reason why, and then I guess we make a Taylor approximation that V, or kind of order V over C, so we're assuming that V is less than C, right?
Yeah, much less
like
than C.
Much less than C to make these
Yes.
approximations,
Right.
because otherwise we don't recover classical mechanics, correct?
Yes, if the speed is close to the speed of light, the mechanics will be different. That's sure. Yeah. Yes, yeah. So classical mechanics is only asymptotic, sure. For small relatively to the speed of light. Yeah, that's absolutely true. Yeah. So I think in particle physics, these formulas cannot be used. You should use really the square root, and because our particles could move very fast.
Yeah, and then can you just re-explain for me one more time, like, okay, when we take the Hamiltonian and we add the Legendre transform of the Hamiltonian together, we look at the contact set. So if you look at like H plus H of X plus H star of Y is equal to XY, can you interpret physically the contact set there in terms of, the Hamiltonian can be interpreted as the energy, right?
Yes.
So how would we physically interpret that contact set?
Right. So in dynamics, the energy is simply half of the work of the forces. Look on this picture, we have, this Hamiltonian is the upper part, the Lagrangian is the lower part, and the areas of them are equal. In physics, when we're looking on statical relations like force, like current versus voltage, if you increase voltage, current will not grow indefinitely. It will be so. If you look on this voltage, this current J and the voltage V, then expression will be like this. Then the energy would be here, the Lagrange transform, Legendre transform, Hamiltonian will be here, area of this one, and the sum of these two areas would be the work of the charges. So that's, but in many, since the most usual applications is dynamics, then it is sort of confusion that usually energy is always half of the work. It is basically because we have kinetic energy. I mean, kinetic energy T is 1/2 of VA, supposed to be V, and when we solve this, so because it's quadratic, so P is AV and V is A minus 1P, linear relations. If the relations are linear, then we're talking about upper and lower triangle, which have the same areas. In continuum mechanics, it's not the case. It's nonlinear continuum mechanics. We always look on this energy. It's not linear. Complementary energy is not equal to the original energy, and that's different from dynamics.
Is there any way to view this Legendre transform as having some special symmetry attached to the Minkowski geometry, or attached to some, I guess, trying to connect the geometric interpretation of the Legendre transform to the relativistic action, right? Like, what's the connection there?
Frankly, I don't know. Well, the easiest way is, of course, to just look on the whole system with the square root and do the Legendre transform and see what will happen. I haven't done it, but it is definitely can be done, I guess. I can just take a Legendre transform with respect to this function, and it will be something. So constant multiplied by square root, we solve for square root. Take PR, you say, whatever, some function, some VR, multiply by square root of 1 minus u prime v square, okay, c square. And so dpr dv, compute dpr dv is vr. V divided by c square with minus sign, and then 1 over square root of 1 minus v square over c square, right? That's the derivative. V square multiplied by this quantity. And we call it P. Okay, PR. And then we need to solve this equation for P. And find V of P. So I just put c square over v square in the denominator, c square over v square minus 1, p not plus p, and compute p r square, which will be 1 over c square minus v square divided by c square here, and then solve for v square and find the relativistic impulse, and then express everything through relativistic impulse. So it is possible, but it will be different than. So when c is very, very large, we definitely in this formula actually we see that p square is equal to v square. But otherwise it will be, yeah. I think it's possible. Yeah.
It's a good exercise to the.
Yeah, good exercise. I don't know. I mean, haven't done this, but definitely, I mean, it's monotonic function. If it's monotonic, you can do it.
Right.
It's a good exercise, yeah. But in principle, you can exclude v as a function of p, and and that will be relativistic Hamiltonian. Yeah. And to check, you need to say that if this p is proportional to v, if p is small, it should go to classical Hamiltonian. Yeah. It's a good question, yeah.
All right, well, thank you so much, Professor, for your time. That was awesome.
Thank you, yeah, that's